Hello, can you hear me well?
Yes.
Yeah.
Okay, great. Okay, so have you read the paper, right? You read the paper already?
Yep.
Okay, so what?
Are you talking about the one which is due yesterday?
Yes.
Yeah, okay.
And today we're gonna learn more about that. I clarify everything on that paper, just a part of that, okay? So, okay, let's start. Last Thursday, we say about what is feedforward neural network and how a feedforward neural network works, okay? And then we introduce the concept of reachability and verification for feedforward neural network, okay? And then we also summarize some fundamental information about polytron. So what is the polytope, convex polytope, how to do some basic operations on polytope using MBT toolbox. And we also consider the core steps in reachability analysis for feedforward neural network, okay? So today, we're gonna focus more about reachability analysis, which is the reachable set computation of a feedforward neural network using a polytope, okay? So today, we're gonna focus on this problem. Okay, so we know that the core step for reachable set computation of a feedforward neural network reduced to the problem of how to compute the reachable set for a single layer with a single input set, okay? Then there are two steps to do that. First, we need to do the R5 mapping of the step one is we do the R5 mapping of the input set using the weight matrix and the pi factor of the layer, right? And then after that, we consider how to apply the ReLU operation on a set, okay? Because we already know how to perform the R5 mapping on a polytope, so we already done with the step one, right? So today we're gonna focus on how to apply the ReLU operation on our polytron, okay? So that's gonna be the core step for today. Okay, any questions? Okay, good. So, okay, so I'm gonna take a very simple two-dimensional example to illustrate how we can apply a ReLU operation on a set, right? So consider this example, we have two-dimensional polytron, and then we can decompose this polytron into 4 regions, theta 1, theta 2, theta 3, and 4, okay? And then our input set is gonna be the union of these 4 regions, right? And then the questions here is that how we compute the reachable set when we apply the ReLU operation on this polygon. Okay, so now we decompose this into 4 regions, and then we're gonna apply the the ReLU operation on each region. Okay, so let's consider for the θ2 first. Okay, so in this region, can you tell me if I apply the ReLU operation on this region, what I gonna get? How the reachable set gonna look like?
Same thing.
Same thing?
Yeah,
Why?
because the ReLU function gets the x, y equals to x if the x is more than 0.
Yeah, that's correct. Right here. So because in these regions we have x1 and x2 is larger than 0, right? Then when we apply, we got the same thing. That means if we have the ReLU operation on these regions, we got the same. The output set is the same as the input set, θ2. Okay. Now let's consider for the other case. So what do we get here? So if I apply the ReLU operation on θ1, so what do we have?
0, a point. Yeah.
0 for x1.
Yeah, 0 x2 there.
0 for x2 or x1?
0 for x1.
S1 and x2 the same, right?
Yeah, remains the same.
Okay, so that means if we apply the ReLU on these regions, we're gonna have 0 and x2, right? In terms of visualization, this is what we have. So how you express R1 in terms of θ1? It's our phi mapping, right? How you express θ1 in terms of θ1? It's gonna be an R5 mapping, right? And in this R5 mapping, the row corresponding to x1, the first row, is gonna be 0 and 0, right? So you always have 0 output for x1, and you have x2, keep the same, right? That's the R5 mapping. Any questions? No questions? You understand? Okay. Okay. I'm gonna see that you are already understand this. Okay. So now go to the third regions. So what do we get?
0, 0.
0 for x1. Are you sure?
x1, 0.
You get x1.
Oh,
x1.
0. Yes.
Yeah. So x1, 0, right?
Shouldn't x2 be 0 since x2 is negative while x1 is positive?
Yeah. So x1 is positive. I think there's some noise. So x1 is positive, right? So x1 is going to be the same. And x2 is mapped to 0, right? So That's the visualization of the set we have, okay? And when you express the R3 in terms of theta 3, what do we have? We have another affine mapping, okay? In this affine mapping, we're gonna project x2 to 0, right? Then we have this line, right?
Zero,
Oh.
zero.
That's correct? Okay. Any questions?
Where does that affine mapping matrix come from?
The affine mapping matrix?
Yeah, the 1, 0, 0, 0. Is that because we're only using that first quadrant?
Yeah, so you can see here. So you keep x1 the same. How do we do it? That means if here you have x1 and x2 here, right?
Right. Because otherwise, if we had 1, 1, 0, 0, you would get x1 plus x2 for the top value, and we just want x1 to return. Okay, that makes sense. Thank you.
Okay, great. Okay, so that's the third region, right? Now come to the 4 regions. So what do we get?
0, 0.
0, 0, right? Okay, great. So that means we, in this case, we get a 0 point, right? And in terms of affine mapping, we have this, right? Okay, so now for this 2-dimensional example, if you apply a ReLU operation on this set, you're gonna have 4 output sets, right? You're gonna have R1 is this segment, R2 is this polygon, R3 and R4, okay? So if I have n-dimensional polygon, then how many polygon is gonna be produced when you apply the ReLU operation?
2 to the n?
2 power n, right? In the worst case. Another question? So
This might be kind of a naive question. Aren't R1, R4, and R3 already included in R2? Because its x is greater than or equal to 0.
So R1 is not included in R2.
Okay, because I thought ReLU was it returns the x value for x is greater than or equal to 0. So it seemed to me like that would include the axis.
No, so you can see in the visualization, right? R1 is a segment that have, like if you have come back to R2 here.
Right.
Here. So R2 is here.
Right. No, I get that it's the axis bound, but what I'm curious about is why that axis bound isn't included in theta 2.
Yeah, in general it's not included, but in some case it's gonna include, right? In some case you're gonna have R1 is a subset of R2. Okay.
Right. That's what I thought it would always be. What case? Let me ask a better question then. In what cases would R1 not be included as a subset of R2?
So here, if you project R2 like theta 2 in x2, and so the maximum point is here, right? If you project theta 1 on x2, if this maximum point is smaller than this maximum point, then you're gonna have R1 is a subset of R2.
Got
right?
it.
When you project here.
Okay, I understand. No, that makes perfect sense. Thank you.
Okay. Okay. So in general, we're gonna have 2 power n polyhedron, right?
Yes.
So you can have some kind of information about when you, here's just a single layer, right? When you count up with several layers, then the number of polyhedrons is gonna explode up, right? So the output of one layer is gonna be the input for the next layer, right? And after a single layer, you already have the input set split into several polyhedrons. When you move to the next layers, it's gonna split again. And then you can imagine that at the final layers, you gonna have a union of polyhedron, right? Which is in general, in the worst case, gonna be exponentially explode up for the number of polyhedron in the reachable set, right? Okay. So now, let's do a little bit coding. So if you already have MATLAB installed and NNV installed, can you do it quickly? So next time, be sure that you can do coding when we are in the class. Okay, I want to make sure that you understand everything in a coding level, right? Do you want me to pass this, or you want to take several minutes to practice how you're gonna do this code? No one answer?
I never got the installation issue resolved from last time. I can try maybe updating or running the script, but when I ran the script the last time I tried to do it, I got, as it was going through the dependencies, I hit a snag with the, where was it? Yeah, it said it.
Startup NNV.
Yep.
So
Yeah,
I'm having
so you got a problem when installing NNV, right?
Yes. Yeah, when I hit in the install script, it's line 29, startup NNV, unrecognized function variable.
Install.
Yeah, in the install.m script, that's a part of the package on GitHub.
Okay,
when you,
so adding dependency, so startup NNV, so we don't have startup NNV here. Oh, I missed the file. Sorry about that. So I'm gonna push the file again.
okay, that's great.
Yeah.
No, that's perfect. That means this is easy to fix. We're good. Thank you. I will just tell me when it's up and I'll pull.
Okay. Okay.
Yeah, thank you.
Yeah. So make sure that you can install NNV correctly, and then next we're gonna practice some coding in the class. Okay. So where's the? Okay. Okay. So here is the video how we can do it step by step. So in this video, I'm going to show you how to apply a ReLU activation function on a 2-dimensional polyhedron. So first, we random generate a 2-dimensional polyhedron in H representation using the built-in function like before. And then we need to consider 4 regions of the 2-dimensional Euclidean space. So the first regions corresponding to x1 is less than 0, x2 is larger than 0. So you can transform to the equality matrix form, like ax smaller than b. So the matrix A here is like this, and matrix B is 0 and 0. Okay, and then you construct a polygon E1, describe the first region. So this polygon is unbounded polygon, right? And then you get the intersection between the polygon you want to apply a ReLU activation function on. You do the intersection between that polygon and the first regions E1. Okay, so you get the intersection polygon T1, and you know that when you apply the ReLU on T1, you got the same T1 because we have x1 is larger than 0 and x2 is larger than 0, right? So that means we have R1 is equal to T1, okay? And then for the second regions, up two-dimensional of this space, we have x1 is larger than 0 and x2 is smaller than 0, okay? And then you construct another polygon E2, and then you get the intersection of P and E2, okay? And now when you apply the ReLU activation function on T2, then what you get? You're gonna do the R5 mapping for T2. You're gonna do the R5 mapping of T2 with the matrix W2 divided by this one. So the reason we have this R5 mapping when you apply the ReLU activation function on T2 is because x1 is larger than 0 and x2 is smaller than 0, right? So you need to project x2 to 0 when you apply the ReLU activation function on this set, and you keep the same x1, right? That's why you have the R5 mapping matrix is W2 equal to 1, 0 and 0, 0. Okay, that means you project x2 to 0 and you keep x1 the same, right? So similar, you consider the third region and the four regions. So the third region is going to be x1 is smaller than 0, x2 is larger than 0, and the four regions is x1 smaller than 0 and x2 is smaller than 0. So for the four regions, when you apply the ReLU activation function on the intersection of P and E4, you're gonna got only 0 right here because you have both x1 is smaller than 0 and x2 is smaller than 0. And then you're gonna have the reachable set after you apply the ReLU activation function on P is equal to R1, R2, R4, and R3 and R4. Okay, and then you're gonna plot the figure. So you plot the original P, the original polygon P, and then the reachable set R here, which is yellow color. So let's see it. So you can see P is the red one here, right? And then when you apply the ReLU activation function on this P, you're gonna got this segment, and this triangle, and the 0 point here. Okay, so that's how you apply a ReLU activation function on a polygon, two-dimensional polygon. Thank you. So in this video, okay. So that's is very simple example how to do the ReLU operation on a polygon. So I'm gonna assign an assignment for you. The due is next week, I guess. So you do the same thing. Generate randomly three-dimensional hex representation polygon, and then you write a function to compute the ReLU operations on that polygon, and then visualize. That's okay? Any question?
The due is on Thursday, I think.
Yeah, Thursday.
Okay.
Easy? I'm gonna update NNB soon, so you can download and install NNB, and then you can start working on this problem. And on this Thursday, we're gonna have like a coding day. Okay, so you're gonna have one class, and then you're gonna combine all things you already learned, and then try to do the analysis for a random generated feedforward neural network. So that's our class objective. Okay, so let's move on. So now when we generate to n-dimensional polyhedron, here are several questions I want to ask. So first, how many polyhedron subsets need to be considered in the worst case? So you already answered these questions, right? It's 2 power n, right? And then, how many intersection operations need to be done in the worst case? Any answer? No answer? So you see my code already, right? When you split off a 2-dimensional polyhedron into 4 regions, you need to, how to do that? You need to get the original polyhedron intersect with some unbounded polyhedron, right? 4 bounded polyhedron, right? So that means the number of intersections here is 4, right? And then in the worst case, when you have n-dimensional polyhedron, then the number of intersections you need to do is also 2 power n, right?
Yep.
Okay, yeah, one answer, good. So the reason we care about this because finally we're gonna come up with the scalability issue, okay? The intersection operation in polyhedron is very expensive operation, okay? So you can see we just play with some toy network, right? Very small number of neurons and small number of layers. And then the polyhedron approach work for that. However, when you increase the number of when you increase the number of neurons at each layer, then the dimension of the polyhedron is going to be increased, right? And then the intersection operations become very expensive. So if you have a H representation, when you do intersection with some half space, it's very easy because you can add the constraint on the H representation. However, when you come up with R5 mapping, it's usually transform the H representation to V representation for R5 mapping operation, right? And then when you come to the net layer, when you do the intersection again, it's gonna transform back from V representation back to H representation to do the intersection operation. The transformation between intersection and V representation, between the H representation and V representation is expensive, okay? So that's why we need to ask this question. Just keep in mind that, okay? And then the same, the R5 mapping operations we need to do is also exponentially great, right? And then when we do intersection operation, so there's the case that you're gonna got an empty set, right? Because if you have a polyhedron, for example, 2-dimensional polyhedron, and you know that x1 is always larger than 0, okay? Then you do the intersection with the space where x1 is smaller than 0 gonna give you an empty set, right? So to check whether the intersection is empty or not before you apply the R5 mapping to get the output set, you need to check the empty set. You need to check if the set is empty. So the number of these empty set operations also explode exponentially, right? And then the last question is how you minimize the number of intersection operations in reachable set computation. Do you have any idea? So basically, the intersection operation is expensive. So it's gonna be more efficient if we can minimize the number of intersection operations when you compute the reachable set, right? Is there any way to do that?
Combine polytopes.
Combine polytopes. Can you explain more?
You could over approximate, you could minimize the number of operations by minimizing the number of polytopes. And you could combine polytopes by taking some convex hole around a set of polytopes to combine them into like one over approximation.
Okay, very close. So here, to compute the reachable set, we split the polytope, right? And now you say, so the convex hole operation is also very expensive, right? Okay, so the easiest way to minimize the number of intersection of operations is that we know beforehand which one is larger than 0, which one is smaller than 0, right? So that means when you get a box contain a polygon, you're gonna know that from that box, you're gonna know that whether or not it's contain a 0 point or not, right? For example, you know for sure that x1 is from 1 to 2. That means you don't need to consider the intersection with the space where x1 is smaller than 0, right? Because x1 is always larger than 0. So if you got a box, I mean, in the optimal way is that if you got the lower bound vector of all the dimensions, you're gonna know that whether or not it's smaller than 0, okay? And if you get the upper bound, you know that whether or not it's larger than 0. So if a dimension contains a 0 point, that means it's made smaller than 0 or larger than 0, then their splitting happened there, right? And that's where we need the intersection operation, right? That's clear? Do you need me to explain again one more time? Okay, so you're gonna see how to minimize the number of intersection when we try to improve the scalability of this approach, okay? Now let's move on. So how to speed up the reachable set computation? Any idea? From the paper you read? No answer? Okay, so one way to speed up the reachable set computation is using parallel computation, right? So you know that for one region, we split into 2 power n regions, sub-regions. And then you can apply the ReLU on these subregions in parallel, right? And then you do everything is parallel. That's the way you can speed up the reachable set computation time, right? Okay. Any questions so far? Okay, so when it comes with technical things, then this may confuse you, right? And another question is that, is there any other ways to compute the reachable set? So here we, from one big polyhedron, we decompose to sub-polyhedron, right? And then you apply the step operations on these sub-polyhedron. And I'm gonna show you that there are another ways, more efficient ways to compute the reachable set to apply the ReLU operation on a polyhedron. Okay, it's called step ReLU methods. Okay, so what is the step ReLU operation? So the step ReLU operation is we apply the ReLU activation function on a specific dimension. So here I define the ReLU I mean when you apply the ReLU activation function on xi. Okay, don't care about x, the other dimension, just care about single dimension here. Okay, so let's see how it works. So when I want to apply the ReLU activation function on x1, so what I need to consider is that we need to consider two cases. The first case is x1 is larger than 0, okay, and then the second one is x1 is smaller than 0, right? Only two cases. Okay, so then if I consider for the first case, x1 is larger than 0, then if I apply the ReLU activation function on x1 dimension, what do you got? You got the same set, right? Is that true?
Yes.
Very simple, right? Because we know that S1 is larger than 0. So here you have a tutor R1 is I call intermediate reachable set. Okay. You only apply the ReLU activation function on x1. Okay. And now if I apply for the second case where x1 is smaller than 0, what do we get?
0.
Yeah, we're gonna get x1 is equal to 0, which is we get a 0 projection for x1, right? Here. Okay. We have this segment. And this segment is our phi mapping of theta2 here, where we project x1 is 0. Okay. And now, so after the first step ReLU operations on x1, we got two sets, right? We got 2 to R1 and 2 to R2, right? And now we take this set to apply the step ReLU operations on x2. Okay, we're gonna do the same way, but for x2. Okay. Now the question is that what do I get after I apply the ReLU operation, the ReLU activation function on x2 from the intermediate reachable set I got after the step ReLU operation on x1. Okay, that's the question. So here we have two cases. So we have tutorial R1. Let's consider tutorial R1 first, okay? Here, we also need to consider two cases. The first case is x1 is shorter than 0. Okay, then you apply the step ReLU on this set. What do you get?
X2.
You get the same, right?
Same.
Okay, and then in the other way, when you have x2 smaller than 0, you got this subset, and then you apply the step ReLU on this subset. What do you get?
Just x1.
Yeah, you just get x1, right? X2 is going to be 0, right? That's what you get. Okay. Any questions? No question. Okay. So that for the first intermediate reachable set. Now consider the second one, right? Here we also consider two cases. The first case is x2 is shorter than 0, okay? And then you're gonna got this set, right? When you apply the ReLU, the step ReLU on x2, you got the same set, okay? In the other way, when you have x2 is smaller than 0, you get this set, right? And then you apply the step ReLU operation on this set, you're gonna get a 0 point, right? So, in summary, when you apply the step ReLU operations on each dimension, sequentially, you can compute the reachable set, right? Here, you got the same result. Any questions? No question? Is it hard?
Computationally, how's this more efficient?
Okay, very good questions. To know if it's more efficient, you need to, okay, so first, you can avoid some unnecessary intersection operation, right? The second things it's gonna come later, that in this way you can do verifications very efficiently. I'm gonna show you later why it's efficient. Okay, so basically from a single polyhedron input set, after, well, it's very hard to explain in this way. However, the methods using step ReLU operations can help you to neglect some unnecessary intersection operations when you do the computation. That's the first thing. The second thing is that when you come to visualize verifications, the methods using step ReLU operations can help you to do deep first search, right? So you can see that from if you have a neural network, you have a single input set. After each layer, it's gonna generate a bunch of polyhedron for you, right? After layer by layer. So using the step ReLU operation approach, you can just deeply search if you have a single polyhedron input set, after the first step ReLU is gonna generate 2 polyhedron, right? And then you just take one of 2 polyhedron, do it again, and get to another polyhedron. and you go deeply to check if the final polyhedron intersect with the unsafe regions or not. If this intersect with the unsafe regions, you stop the algorithm very quickly. You don't need to worry about the other branches, right? You just search deeply, like you use deep first search approach here, and then you can quickly prove that the neural network violates the safety property without searching the other branch. Do you get what I mean? So it's gonna come to so we discuss the reachable set computation first, and then we're gonna discuss how we do verification. It's a very interesting, right? There are two ways to do that. The first way is that you can compute layer by layer all the reachable set, and then you at the end you're gonna have all the reachable set, and then you verify all of the reachable set whether or not they are intersect with the unsafe regions or not. If it intersect with the unsafe regions, you say the network is unsafe, for example. However, there are another way to do it more efficiently. Okay, so you don't need to compute all the reachable set of the network corresponding to a single input set. You only compute a branch of that reachable set and then check if it's violate the property or not. If it's violate the property, you stop and you give the answer is unsafe without searching for the other branch. Okay, do you get what I mean? So I gonna describe in detail in the verifications in the verification session. Okay, for now we just I just can describe very briefly why this method is better. Okay, any other questions? No. Okay. So so you know that we can compute the ReLU operations on the polyhedron by executing a sequence of step ReLU operations, right? And keep in mind that after one step ReLU operation, a single polyhedron can split up into two polyhedrons, right? And you can see that the number of polyhedrons explode exponentially when you execute a sequence of step ReLU operations, right? So in general, when you have n-dimensional polyhedron, then the ReLU operations can be done by performing a sequence of step ReLU operations on all dimensions. Okay, that's how we do the generalization. So that means the call step for ReLU operations is gonna be the step ReLU operation. Okay, we only worry about a single dimension at one time and how it's worked, and then we apply it recursively for all the dimensions. Then we finally get the output of the ReLU operation. Okay. Any questions so far? No.
I was going to ask, does this ability to break the ReLUs up into step ReLUs, does that apply to any other activation functions?
Yes.
ReLU?
Yes, you're gonna learn the other activation function later, right?
Okay, so this is actually like a general strategy you can use, this depth first search.
Yes.
Cool.
Yeah.
Thank you.
Okay. So you're gonna see that the polyhedron approach is not good for 6 more and 10H. Okay. However, the star set approach is very good. So you're gonna read the star set approach soon. But before we come to the star set approach, I want you to have a general idea how's everything works. So, and why is the polytron approach is not scalable, and why we need to use another approach called star set. Okay. But in general, after this first approach, you're gonna see all the problem in reachability analysis and verifications for the neural network. I haven't mentioned about another type of activation function yet, but you're gonna learn it when you come with the star set methods. Okay. Okay. So coding second. Coding 2. So write a step ReLU operations function. So the input is n-dimensional polytron, right? And the specific dimension index where we apply the step ReLU operation. And then the output of this step ReLU function is going to be an array of polytron. Okay. So basically, I want you to write this in this class, and you can ask questions. However, because most of you doesn't have NNB installed, so let's skip this time, okay? But next Thursday, hopefully all of you already have NNB installed, and then we can practice this approach in the class, okay? Okay, so I'm gonna show you how to do it. So basically, the function I want you to write is step ReLU, and it's gonna have an array of input set here. Here you just consider for single input set first. And then the ID, which is the dimension index where you want to apply the ReLU activation function on, okay? And then, okay, so here is the video, how to do it. So in this video, I'm gonna show you how to implement the step ReLU operations on a specific input set. So the input to the step ReLU operation function is an polytron I, and the index, that means the specific dimension where we apply the step ReLU operation. So the output is an array of polytron in general. Okay. So first, what we need to do is we need to check if the input is a polytron object or not, and we check if the index is valid index or not. So here we have I dot dim, that means the dimension of the polytron input, right? So if the index is smaller than 0 or the index is larger than I dot dim, that means the index is invalid. So if we have the input set is empty, then the output set is empty. Okay. Otherwise, we need to consider two cases. The first case is that we consider x index is larger than 0. So in this case, we need to create a polytron to describe this case, right? So this polytron specify for x index is larger than 0. And then we get the intersection of the input set and that polytron specifying for the first case. Okay, and then we check if the intersection is empty or not, is the empty set or not, because there is maybe the case that the x index is always smaller than 0. Okay, here. So if it's not empty, then we know that when we apply the ReLU operation function on this specific dimension, then we got the same. We got the output set is the same as the input, right? So in this case, R1 is equal to T1. Otherwise, if it is empty, then we have R1 is empty, okay? And in the second case, we consider x index is smaller than 0, Similarly, we construct another polygon, specify dash regions, and then we get the intersection of the input set with dash regions, and then we define an affine mapping matrix. So this affine mapping matrix basically trying to project the output corresponding to x index is smaller than 0 equal to 0. Okay, so you can see it keep another dimension the same, right? And then the dimension dimension with the index, the output corresponding to the dimension with this index is equal to 0. Okay, and then again we check if this intersection is empty or not. If it's not empty, then R2 is the affine mapping of T2 with the affine mapping W2 we already construct. Okay, otherwise it's equal to empty, and then we combine them together to get the intermediate reachable set for this step ReLU operation. Okay, so that's how the function works. So let's see. So here we generate a polygon P, okay, 2 dimension, and then suppose we want to get the intermediate reachable set if we apply the step ReLU on the first dimension x1. Okay, we're gonna plot this. Okay, so you can see here that this one is the polygon input set P, and then the yellow one and this segment, so 2 polygon, is the output, the intermediate reachable set after we apply the step ReLU operation on the first dimension here, this first dimension. Okay, so that's how a step ReLU operation function works for specific input set. So in this video, any questions? Okay, good. So how we write the ReLU operation using the step ReLU operations. Keep in mind that after one step ReLU operations, a polygon might be split into 2 polygons, right? And then when you come to the next step ReLU operation, you need to have the ability to handle all like multiple polygons at the same time, right? So in this function, you can see I have a ReLU function. I is a single polygon, and then I'm gonna perform the step ReLU operations on all dimensions. Okay. However, what I call here is that I call the step ReLU with multiple inputs function, and this function's gonna call the step ReLU for each specific input. Okay, so here suppose we have n after the first step ReLU operations we have n polygon, and then we're gonna call the step ReLU for this n polygon with the same index. Okay, so that's how we can implement the ReLU operations using the step ReLU operations. Okay, and let's see for the video here. So in this video, I'm gonna show you how to implement the ReLU operation using the step ReLU operations. Okay, so basically, when you apply a ReLU operation on the input set, on a polygon input set, you can get the results by transform the ReLU operation to a sequence of step ReLU operations. Okay, so you're gonna get the step ReLU operations through all the dimensions and then get the final output set. Okay, And the problem here is that for a single polyhedron, after a step ReLU operation, you can get 2 new polyhedrons, right? And then when you have a sequence of step ReLU operations, the output set, the intermediate output set of a step ReLU operations, going to be the input set to the next step ReLU operation, right? And because the output set of a step ReLU operation might have like several polyhedra, and then when it comes to the next step ReLU operations, the next step ReLU operation needs to be able to handle multiple inputs at the same time, right? So here, the core idea of the ReLU operation function is that you're gonna call the step ReLU with multiple inputs, right? And you go through all the dimension and get the final output set R1 here, okay? And the step ReLU with multiple inputs just call the step ReLU with a single input for all the input set contained in this input array, okay? So that's how it works. So let's see, for this example, I'm gonna generate a 3-dimensional H representation polyhedron P, and then I'm gonna apply the ReLU operation on this P, okay? Okay, so here is the result. So we have 3-dimensional, you can see the yellow one is the output set after you apply the ReLU operation on the input set B. So here, okay. And then you can check R. So R is an array of A polyhedron, okay. And I think that is for the ReLU function using the step ReLU operations. So in this video, okay, so you have the homework, right, for 3-dimensional polyhedron, and apply the ReLU operation on that polyhedron. You have that homework. I already showed you in the video how to do it using step ReLU operations. Just keep in mind that you can use the original one, like you just split the input set into 9 regions and then perform the ReLU operations on each region, okay? That's the other way. And in the video I just showed you, I use step ReLU operations, okay? And now we already handle the ReLU operations. And now we come back to see how we design the reachability algorithm for a layer, okay? So for a layer, we have a way and the bias. And the first step is that we do the affine mapping. That's the step 1. And then we apply the ReLU operations. So the code for the reachability analysis for a ReLU layer is very simple. So we have the weight matrix and the bias factors of the layers as an inputs, and I is the polyhedron input set to the layer, okay? And then you just do the first step, like affine mapping, and then you do R is equal to ReLU of this last affine mapping step, okay? And then you can get the reachable set for a single layer, right? And then if you do again and again, you can get the reachable set for the whole network, right? That's how it works. It's very simple, right? Any questions here? No questions? Okay. So now let's look at this video for the example. So in this video, I'm gonna show you how to compute the reachable set of a ReLU layer using the ReLU operation. Okay, so we have two steps. The first step is the affine mapping step. The second step is the ReLU operation step. Okay, so the input to the ReLU layer reach function is going to be the weight matrix of the layer and the bias of the layer, and then the input set I. Okay, and as we learned, we have two basic steps. The first step is do affine mapping of the input set using the weight matrix and the bias vector. And the second step is going to be applying the ReLU operation on the mapping polygon I want. Okay, then you're gonna get the reachable set of the layer. Okay, so let's see how it works. So I randomly generate a two-dimensional H representation polygon, and then I also randomly generate the weight and the bias for the layer W and B here, and then I call this function to compute the reachable set of the layer. Okay, so keep in mind that for a real neural network, the weight and the bias is the learning parameters. Is learnable, right? So when you train the network, you get the W and the B. Okay, here we just assume that we already have W and B. Okay, and then I plot the figure as normal. So the reachable set is going to be 0, 1. The input set is the red one. Okay, so here is the result. So you can see that the input set in 2D is the red one, and the reachable set for the layers in 3D is the yellow one. Okay. Okay, so that's how we can compute the reachable set of a ReLU layer using polygon. Okay, and next we're gonna consider how we extend this for a feedforward neural network, which is very simple. Okay, so this. Okay, so another coding assignments is I want you to randomly generate two-dimensional H represent polygon, and then we generate randomly a feedforward neural network with the following architecture: 2 times 5 times 5 times 5. So that means you have two inputs, two outputs, 3 hidden layers with 5 neurons per layer, and then you write a function to compute the reachable set of the network you generate with the polyhedron input set. Okay, so that's another homework for you to do. Any questions? And yeah, so I think it's gonna be all for today. On Tuesday, no, on Thursday, hopefully we can show this coding assignment in the class together. Okay, I want to make sure that all of you can implement this simple example, and then before we move into another problem, like before we move into verification problem. I think I gotta update the NNV and the installation part, and make sure that you can install NNV correctly, and then let me know if you have any questions or any concern about installation. So any questions? No questions?
Mr. Chen, are we gonna have the planned appointment here in the chat or somewhere else? You're gonna send the link.
Sorry?
Are we gonna have like the planned appointment in all the office hours here in the chat?
Yeah.
Okay.
So you want to ask me something, right?
Yeah. Sure,
Yeah, I think you can. We can use this link after the class if you want to ask something.
All right, cool.
Okay. So any other questions? Okay. So before we end this class, I'm gonna show you how to show this homework. Okay. Okay. So here's how I do it. Oh no. Okay. So before we go to the video, just briefly, I'm gonna summarize some important information for the class today. So first, the core steps in computing reachable set of ReLU layers are file mapping, intersection, and ReLU operation. Okay, and all of them also time is expensive. Okay, and time in consumption steps. Okay, and then the ReLU operations can be done by a sequence of step ReLU operations. And you already learn how to do step ReLU operations for specific dimension, okay? And then the ReLU operations on n-dimensional polyhedron creates, in the worst case, 2 power n new polyhedron, okay? And then from this approach, you can see that the exact reachability of a ReLU layers is decidable. What does this mean by decidable? That means you can do it exactly. You can write an algorithm to do it exactly. However, it's going to be an NP-hard problem because the number of polyhedron is go up exponentially. Okay, so that means you have no way to design an algorithm that have polynomial terms to compute the reachable set, to exactly compute the reachable set for a feedforward neural network with ReLU activation function. Okay, and then yeah, so that's what I just said. Verifications for ReLU feedforward neural network is an NP-hard problem because when after you compute the reachable set, you need to make sure that all polyhedron in the reachable set satisfy the safety property. That means in the worst case, you need to check 2 power n polyhedron violates the property or not. So that's why it's an NP-hard problem, right? And the last questions, keep in mind that how we can speed up the reachable set computation time. Okay, that's going to be a core focus, the main focus for our next several class, right? How we can improve the polyhedron approach using star set, and how we can improve the computation using parallel computation, parallel computing toolbox in MATLAB, and then how we can minimize the number of step ReLU operations when we do the computations. Okay, so all of these topics gonna be covered on next week, I guess. Okay. Okay, so I think that's all for today. I not gonna show you the video how to show the homework. However, hopefully you're gonna show me how to do it by yourself next Thursday. Okay. Okay, I think that's all for today. Thank you. Any questions?